In the last section, we examined to see what happens to a value of a function as x gets very, very large. In this section, we're going to look and see what happens to a value of the function as x gets close to a finite number. And we'll start this discussion by looking at the concept of instantaneous velocity. And in a particular case, when we have a falling object. Galileo's law says if air resistance is neglected for an object in free fall, and if the distance that the object falls after t second is denoted by s of t and measured in meters, then we can find that distance using the formula s of t equals 4.9 t squared. And 4.9 accounts for the gravitational pull of the Earth. And once again, we assume there is no resistance due to air. Now, what we are going to be looking at in a particular instance is what happens if I drop a ball from the top of a skyscraper and we want to find the velocity after 4 seconds. And what we mean by that is what the velocity is exactly after 4 seconds. Now, we can find the velocity over a length of time. I can find the average velocity. The average velocity can be found by finding the distance the object has traveled, the change in its position, divided by how long it took to travel that distance, the time that is elapsed. Right, so I can find the average velocity over a 0.1 second, so from 4 seconds to 4.1 seconds. Here's the formula for finding the average velocity. So I find the position after 4.1 seconds using Galileo's law. So I have 4.9 times 4.1 seconds squared minus the position after 4 seconds, 4.9 times 4 squared, and then divided by the time elapsed, which is 0.1. That gives me 39.69 meters per second. So the average velocity for the 0.1 second is 39.69. Except this object is not constantly traveling at the same speed or same velocity. So if I looked at this average velocity over a shorter period of time and used from 4 to 4.01 seconds, we'll see that the average velocity is now 39.249 meters per second squared. And if I go from 4 to 4.001 seconds, so in a shorter period of time, the average velocity changes again to be 39.2049 meters per second squared. And once again, each of these pieces calculates the distance or the position of the object. And then when I subtract them, I can find the change in position or the distance the object had traveled. And on the bottom, I have the time elapsed between the two time periods I'm looking at. And finally, if I make this time a little smaller and I go from 4 to 4.001, the average velocity is going to be 39.20049 meters per second squared. And we can kind of see what's happening here as my time interval gets smaller and smaller. I will get an average velocity that's getting closer and closer to 39.2. And it turns out that the actual instantaneous velocity after 4 seconds is exactly 39.2 meters per second. Right? And that brings us to the concept of limits and the notation that we have for a limit, right? So as in this case, as my value is getting closer and closer to 4, the limit for the velocity, we say, is 39.2. So as a notation, this is the definition that we use. So if I have a function that's defined when x is near a, so in our last problem, when my x value or my time was near 4 seconds, and my function needs to be defined in an open interval that contains a, except possibly at a itself. So as we look at our functions, we are going to look at values that are close to 4 seconds, for example, but not 4 seconds itself. Then this is what we will write. Limit as x gets close to a of f of x, or limit of f of x as x approaches a is L. So we write this notation if we can make the value of f of x arbitrarily close to L. That means no matter how close we want to be, I can find the next value that will let me get that close. Right? So by taking x's to be sufficiently close to a on either side of a, but not equal to a. Right? So in our last example, we only looked at values that were bigger than 4, but for me to say there is actual limit, I would need to also consider values that are smaller than 4. Right? So in general, what this means is f of x is going to approach L. F of x gets closer and closer to this limit L as my x values get closer and closer to a. So let's look at an example. So suppose I want to know what happens to x multiplied by cosecant of x as my x gets closer to 0. I want to estimate that value. So to start with, let's first examine this function. If you recall, cosecant of x is the same as having 1 over sine of x. And sine of 0 is equal to 0. So if I tried to plug in 0 into the function x cosecant of x, I would have 0 times 1 over 0. And 1 over 0 is undefined, so this function itself would not be defined at 0. And that's why we usually are interested in the limit, because the value of the x itself is not easily attainable. Or the function may be undefined at that point, but we could use numbers that are very close to it as a indicator of how the function behaves. Okay, so if I go ahead and use Excel to figure out different values, this is what I get, right? This is what I got when I plugged in the function x cosecant of x, programmed it into Excel, and used these different values of x. So when x was -1, the value of x cosecant of x is 1.188395106. And as I got closer and closer to x being 0, so in this case x is getting gradually smaller and getting close to 0, you will notice what's happening to the value of the function. The value of the function is getting closer and closer and closer to 1. And if I also look at x values that are bigger than 0, we'll notice a similar pattern. As my x gets closer and closer and closer to 0, the value of the function, again, is getting closer and closer and closer to 1. And that somewhat indicates that that limit is probably 1, right? If I estimate it, I can tell you it is 1. I can't tell you it is exactly 1 until if I get even closer to 0, and maybe in future chapters we'll find algebraic ways that this could be evaluated. But for now, we're going to just rely on these values and may look at the graph. So here is the graph of the function that we were looking at, x cosecant of x. And if I now zoom in at 0, so the closer my x values get to 0, we'll see that that function is getting closer and closer to being equal to 1. Notice there is an open circle at 1 because the function itself was undefined. But I think at this point we can say that the limit as x goes to 0 of x cosecant of x is going to equal to 1. As x gets close to 0, the function itself is getting arbitrarily close to 1. Right, so here is another example. We're going to look at x squared cosecant of x. Now, as before, we have the same issue, plugging 0 in the function itself would not have given us an answer, and that's really why we're interested in its limit. And if I follow the same process that I did, if I look at the values of the function as I plug in those x values into x squared cosecant of x, these are what I would get. And notice in this case, the value of the function is not getting closer to 1. In fact, it's getting farther from 1, and it's getting smaller and smaller and smaller, and getting close to 0. Just to check at the other side, when I have numbers that are bigger than 0 and I'm plugging them in, the closer to 0 I get, the smaller the values get. Right? So in this case, it looks like x squared cosecant of x is approaching 0. The limit is x squared cosecant of x approaches 0 as x gets close to 0, or as x approaches 0. And once again, if I can verify this by looking at its graph, that's what the graph of x squared cosecant of x looks like. And if we zoom in, the closer to 0 we get, the closer the value of the function gets to 0. And once again, there's that open circle because the function itself is undefined. So limit of x squared cosecant of x as x approaches 0 is equal to 0. Okay, so let's look at some of the definitions. So as you notice, as we were doing these limits, I was looking at what happens when I get close to a certain x value, but from both sides. So it's slightly smaller, slightly bigger values to see if we get the same answer. And that's what the concept of one-sided limits all about. So by definition, we use this notation where I have a limit as x goes to a, but a has a negative exponent. Well, it's not an exponent, but has a negative superscript on the top. When we use that notation, we say that's a left-handed limit. And that means when I plug numbers in, or when I look at the graph, I'm looking at the part of it that's to the left of a, where the numbers are slightly smaller than a. And by the same logic, if I use a superscript of a plus, that means we have a right-handed limit. We're approaching our x values as being slightly bigger than a, or on our graph a little to the right of a. Okay, and for us to actually say a function has a limit as x approaches a, we must have both the left limit and the right limit equal to the same value, right? So limit as x goes to a of f of x equals L. We say it's equal to some value L if and only if both the left limit and the right limit are equal to L. Okay, so saying that a limit is equal to L is equivalent of saying the left and the right limit are equal L, and vice versa. If I say the left limit is L, right limit is L, that means the limit of the function itself is equal to L. Okay, so next thing we're going to define is what we mean by a limit to be infinite. So by definition, if a function's defined on both sides of a, except possibly at a itself, and again, remember we're looking at numbers close to a, not a itself, then we say limit as x goes to a of f of x is equal to infinity when the value of f of x can be made arbitrarily large as we want, by taking x's sufficiently close to a but not equal to a. So If there are x's I can plug in close to a, that make my function be a billion or a trillion or however large I want it to get. If I can do that, then we say the limit is infinity. And we say it's negative infinity if I can make it arbitrarily large negative. Negative a billion, negative a trillion, and so on, right? So if I can make it as large as I want to be a negative large number by picking numbers close to a, we say that the limit is negative infinity, right? So let's consider an example here. So here's the function I have, x over x minus 3 squared. And once again, if I plug in 3 itself into this function, I'm going to have a 0 on the bottom of the fraction, which makes the function itself undefined. But I can see what happens if I get close to 3. So what happens if I don't plug in 3 itself, but plug in numbers very, 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 very close to 3? And to start with, if I look at the chart, if I approach 3 from the left, so by going using numbers smaller than 3 but getting closer and closer and closer, you'll notice that this function keeps getting larger and larger and larger in its value. And just to check on the right hand side, if I approach 3 from the right, so pick numbers that are slightly bigger than 3 and get closer and closer and closer and closer to 3, we'll notice that again the values of the function keeps getting bigger and bigger and bigger and bigger. So it looks like this function keeps increasing in its size without bounds. And if I consider the graph of this function, once again, if I zoom in, you don't see much. So if we zoom back out, we'll see that as x, if the numbers were close to 3, this function would be getting larger and larger and larger. And it can be arbitrarily large the closer to 3 we get. Therefore, we say that the limit of this function as x goes to 3 is infinite. One other example to consider in this case, so we have a limit as x goes to 3 of 5 over x minus 3 cubed. And once again, looking at the values, as I get close to 3 from the left side, numbers that are slightly smaller than 3, these are what I would get. So notice it's getting extremely large, but negative, right? So it's a very large negative number. And if I approach my x close to 3 from the right side, so if we approach 3 from the right, we'll get similar situation. I get larger and larger and larger values, but in this case, the values are all positive. So here we'll see that the left limit and the right limit are not giving me the same answer for this particular function. Here's what the graph looks like. Again, we're going to zoom out in this case so we can see what happens when we get close to 3. So as we zoom out, we'll notice that the numbers that are close to 3 on the right side the graph is going up, but the parts that were x's, the x's that are smaller than 3 have the function go down and become an extremely large negative number on the left, extremely large positive number on the right. So the left limit in this case is negative infinity, while the right limit is positive infinity. And therefore we say that the limit itself does not exist. If you recall, we said the limit is equal to a number if and only if the left limit and the right limit agree. And in this case, they don't. And just to connect this to concepts we had seen in the past, the last two examples you should hopefully recall from your previous classes as rational functions that have asymptotes. So in these cases, when we have infinite limits, we have functions that happen to have vertical asymptotes. And just to connect the two concepts, we define that a line x equals a is called a vertical asymptote of a function y equals f of x if at least one of these 6 statements true, right? There could be more than one that's true, but at least one, right? So either the limit is infinity, or the left limit is infinity, or the right limit is infinity, or one of those is negative infinity, okay? Or it could be all 3 are negative infinity. But at least one of these 6 facts have to be true for us to say that a line x equals a is a vertical asymptote.